Welcome to Intermediate Algebra. We're just doing a geometry review on this lecture. My name is Roy Simpson. I'm a professor of mathematics at Cosumnes River College in Sacramento, California. The prerequisites that I expect people to have when they're watching this video is that they have some exposure to geometry. You also need to know, obviously, some arithmetic and some stuff from elementary algebra, but this is part of an intermediate algebra review, so therefore it's assumed that you've had Algebra 1 or elementary algebra. We go ahead and start this off with some basic information like what is a right triangle. It's probably easier just to draw one. A right triangle is a triangle in which one of the angles is 90 degrees, and this little square bracket here indicates that that's a 90-degree angle. So one angle has to be 90 degrees. The side opposite the 90 degrees, by the way, is often called the hypotenuse. And the other two sides are called the legs, in no particular order. But definitely the side opposite the 90-degree angle is always called the hypotenuse. And we'll go ahead and just do a little example here. Suppose that the two non-right angles in a right triangle are x and 3x plus 16. Find the measures of each angle within the triangle. Well, obviously one of the angles is measured 90 degrees because it's a right triangle. So let's pretend that this angle right here is angle x. We usually use that arc to indicate that that is an angle right there. And I'll use a double arc to indicate this is a completely different measure angle, and we'll call this 3x plus 16. Now, one of the theorems that I didn't bother writing down, but one of the theorems in mathematics that involves triangles is that the sum of the angles in a triangle must add up to 180 degrees. That is, x plus that 3x plus 16 plus that extra 90-degree angle must add up to 180 degrees. And now as I'm writing this, under the prerequisites I should have said you should know how to solve an equation. So what we'll do is we'll combine like terms or actually clean up the left-hand side by combining like terms. So we'll have 4x plus, looks about to be 106. I'm going to drop off the degree signs for now. Not a big deal to not have them. Subtract 106 from both sides, and we should get 74 on the right hand side. And then divide both sides by 4. You get 74 over 4. And by the way, this is not done. It needs to be reduced, or simplified. So that's 37 halves. And you can actually get an exact decimal representation of this as 18.5. So x, being this angle right here, is 18.5 degrees. So therefore the other angle, which is 3 times x plus 16, will be 3 times 18.5 degrees plus another 16 degrees. Should be about 55.5 degrees. I'll double check that in a moment here. Plus 16 degrees. Yeah. It's 671.5 degrees. We could double check this, by the way. If one of the angles is 71.5 degrees, so that's this angle right here, 71.5 degrees, and if the other angle is 18.5 degrees, well, let's add these up. 18.5 plus 71.5 is 90, and we have an extra 90 here, so that's 180 altogether. That makes sense. The next thing I want to mention here in this geometry review is the Pythagorean theorem. This is the most important theorem. Well, I don't want to say the most, but it is one of the most important theorems in mathematics because it is the basis for an entire course called trigonometry. And the Pythagorean theorem essentially says the following: if you're given a right triangle, and it has to be a right triangle, it can't be like any other style of triangle, it has to be a right triangle. You have a couple legs here, I'll just name them A and B, and the hypotenuse here we'll name C. If that's the setup, then it turns out some of the squares of the legs should equal the square of the hypotenuse. Or in other words, a squared plus b squared is equal to c squared. And this is, like I said, an extremely important theorem. And I'd like to actually prove this because I think that it's important enough that people should be able to understand a proof of it. So let's go ahead and go through and do a proof here. Proof. I'll start by drawing a box first. Specifically, a square. And what I want to do with this square is to kind of create a bunch of little triangles within it. So let's suppose that I want to dice this up, and I'll just do it kind of like this. Make sure these lengths are all kind of the same. That's the important part. Okay. And this one right here. Hopefully this all kind of looks the same. All right. So what I'm going to do is I'm just going to pretend for a moment that we can make a perfect little set of triangles in here, just like that. And we'll have to all agree that these are right triangles that are in here. All these are little right triangles, and in fact, you can see this square in here has right angles all throughout it as well. Although that's not so important for this proof. But this proof is fairly easy to understand once we get going. So what I'm going to say is each of these triangles have the same length. In other words, because this is a square, each side has the same length. And what I did is I essentially said, well, if this side has some length, I don't care what it really is, I'm going to break it up to where maybe this side, this part of it I'll call length A, and this part of it I'll call length B. And then I'm going to cut up the next side to where, again, this side length B and this side length A, this side length B, this side length A, side length B, side length A. Just because I want to. And now I have no idea what this extra side length here is, but we'll call it side length C. And because these are all the same triangles, these C's should all be the same. Okay, they're all the same shape, same size, everything. So you have 4 of the exact same triangles. Now let's talk about how you would find the area of this square. This seems like a highly unrelated question, but it actually relates to this problem quite a bit. So to find the area of this square, we would multiply the length of one side and the length of another. Well, or you could just say I'm going to take the length of one side and then square it, because each side has the same length. So the length of one side is A plus B, and maybe I'll put a little note here. This is the area of a square. Okay, so that's A plus B is one side length, A plus B is the other side length. So therefore, if you know a little bit of mathematics, you know you distribute across parentheses. So you'll have A times A, right? You'll have A times B, you'll have B times A, and then B times B. So that'll be an A squared plus 2 of those ABs plus B squared. So that's the area of the giant square there. Now there happens to be another way to figure out the area of that. The other way to do this is to look at the area of these triangles, and that can be done just by getting the area of one of them and multiplying it by 4, and adding to that the area of this inner square here. So let's do that. In fact, I'll write it in the same ink here. Area, oh, it's hard to read that though. Maybe I'll just go ahead and go back to the purple. Area of center square. Well, this is pretty easy because you can see center square has side length C here and side length C there. So it's just C times C or C squared. And then the area of one triangle, well, the area of a triangle is 1/2 base times height. The base on this triangle, let's just say this one right here, the base is A. The height, well, is this. It's B. So it's 1/2 AB. Of course, we don't just have one triangle, we have four, so the area of four triangles is going to be just 4 times that, 1/2 AB. The 2 and the 4 will cancel nicely to become 2AB. All right. So the area of the square, of the big square, could also have been found just by saying, okay, well, it's the area of the center square plus the area of those 4 triangles. Now here's a quandary. This is kind of an interesting little thing. We have the area of the square as one formula, and we have the area of the same square written as a separate formula. So these two things, this formula or this expression here and this expression here, mean exactly the same thing. So they should be equal. A squared plus 2ab plus b squared should be the same thing as that c squared plus 2ab. Well, if you subtract 2ab from both sides, you'll see that these kind of go away, and you get this wonderful result that a squared plus b squared is equal to c squared. Now, a lot of people don't understand why that proves that a squared plus b squared is equal to c squared, so let's just rewind a moment and ask ourselves, what did we assume about a, b, and c here? What we assumed was that a and b were the legs of a right triangle and c was just the hypotenuse. That was it. That was the only thing we assumed about it the entire time. So if a and b are the legs of a triangle, right triangle, sorry, and c is the hypotenuse, then a squared plus b squared must equal c squared. And that is the end of the proof. Let's go ahead and use this. So in this example, let's just suppose I have a plate of samosas here, and I'm not 100% sure that I spelled that correctly. It's an Indian treat. Suppose that one side of a right triangular shaped samosa is of length x and the other is of length x. If the hypotenuse is of length 3 inches, how long is each side? So that essentially what we're saying is that length right there, we're going to call length x. This length right here, we're saying is also of length x, and we're saying this is a right triangle. And I'm telling you, I happen to know this is 3 inches long right there. So let me draw this out a little more obvious in style. So there we have x and x for the lengths of the sides, and 3 inches for the length of the hypotenuse. And we want to know how, really, what is x? Well, we could use the Pythagorean theorem here. Pythagorean theorem says square one side plus square the other side. That summation should equal the square of the hypotenuse. And let's see, I have an x squared plus another x squared, so I guess I have 2 of those. And that should equal 9. I'll go ahead and divide both sides by 2. And now I get to take the square root of both sides. If x squared is equal to 9 halves, that implies that x must have been the square root of 9 halves. And something that you may have learned in an elementary algebra course or not is that usually, or you might recall this from a previous course, usually you'd write plus or minus here. The fact is that we're talking about x as a length, so I'm only worried about the positivity or the positive value of x. So this will end up being roughly, if I grab a calculator, because we haven't discussed yet, we haven't discussed how to simplify radicals, and that wasn't a prerequisite for this discussion. So how you would do this, you grab your handy dandy calculator, whichever calculator you have. I have a calculator like this. I'll clear off the screen, and then you just type in the square root of 9 divided by 2 and end that square root. You get 2.12, and we'll just round it to the nearest hundredth. So 2.12, roughly. And by the way, since we were talking inches, x would be in inches as well. So each side is roughly a little greater than 2 inches long. Now we'll go ahead and define a couple of styles of triangles, even though I have to admit there's going to be in the future a ton of uses for the Pythagorean theorem. One example suffices for now, just because we're doing a brief review. Equilateral triangles are a special kind of triangles where basically all sides are of the same length, and if all sides are the same length, then all angles are of the same length or the same measure as well. So we denote equal side length with just a single hash there. So all sides and all angles are equivalent. In that case, if you think about it, if you have 180 degrees and you're splitting it equally amongst three different angles, then it turns out that each of them must be 60 degrees. So equilateral triangles are very special, very specific. They all have 60-degree angles. Now the side lengths don't have to be 1, 1, 1. They could be 5, 5, 5, or pi, 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 anything like that. Isosceles triangles are slightly different. So let me go ahead and draw an example of an isosceles. I'll draw an exaggerated example of an isosceles. An isosceles triangle has what's called a vertex angle, and then two angles that are exactly the same. By the way, that's a vertex angle. And the two angles that are exactly the same we call base angles. So I'll go ahead and point an arrow at these two base angles here. 1, 2. And because these two base angles are the same, it turns out their opposite sides are exactly the same as well. But the side opposite the vertex, you can even see in this example, is not the same measure. And the definition essentially is that a triangle where two angles are the same. And this implies that the opposite sides are the same, just like I mentioned. So let's go ahead and take a nice, interesting example here. The flag of East Timor has a flag with an isosceles triangle in it. And I'll just go ahead and show you, let's see, a good color to use on this, maybe blue. I'll show you by highlighting what I'm talking about here. This is one of the sides. This right here is one of the sides. And finally, this is one of the sides as well. Okay. So the flag of East Timor has a flag with an isosceles triangle in it. If the vertex angle, and that's, remember, this angle right here is a vertex angle. That vertex angle is 80 degrees less than twice the base angle. Find the measure of each angle. Okay. So I've read the problem, kind of going back through what I consider to be the way you solve all word problems. You read it and understand what's going on. Second thing is you label your unknowns. So thing I don't know here is I really don't know three angles, but two of them are the same. So I'm going to let x equal the base angle and y equal vertex angle. Those are the two things I don't know. Once I know base angles and vertex angles, I'm done. Third thing we need to do is write an equation for the situation. Well, I know the sum of the angles is going to be 180. So we have a base angle plus another base angle, right? This is a base angle, that's x. This is another base angle, that's x, plus the vertex angle, and that should all be 180 degrees. But we also know something else from what they told us. By the way, let me just combine like terms here. 2x plus y is equal to 180. They gave us that the vertex angle is, vertex angle we said was y, turns into an equals. So y equals 80 degrees less than twice the base angle. Now here's where students get stuck. They want to know, is that 80 minus 2 times the base angle is x, or is it 2x minus 80? And that's a good question. So if I told you I have $3 less than you, that means I have your amount but a little bit less, right? So let x be the amount that you have. If I have 3 less than you, then I have the amount you have but less by 3. In other words, x minus 3. So that type of situation can be used to express that this is the correct way to go about it here. That this is actually 80 degrees less than twice the base angle. So 2x minus 80 is exactly what we need here. Now this is called a system of equations, and I know it's introduced way too early, that I always introduce this way too early, but honestly, I really just like solving problems with as many variables as possible because it gets confusing if I don't have them. So here I see I just label all my unknowns, and then it turns out that when I start building equations, I have the same number of equations as I have unknowns. I have two unknowns, an x and a y, and I happen to have two equations. That's perfect. And what I'll do is I'll take this value of y, I happen to know that y is 2x minus 80, and I'll substitute that in for y here. So in other words, 2x plus y, which is 2x minus 80, should equal 180 degrees. Let's combine like terms here, so I get that 4x minus 80 is 180. Or in other words, 4x is equal to 260. And now I just divide both sides by 4. What is that? 65? Yeah. So I see that x is 65. So that means that these vertex angle or these base angles are 65 degrees. That one is, and so is this one. And what does that mean about y? Well, y, just from this equation right here, y is just twice that, minus 80. In other words, it's 130 minus 80, or 50 degrees. There we go. We found the measure of each of these angles in this flag. By the way, I can't claim that those are the actual angles. I made this up. But that is the flag of East Timor, but I don't know the angles offhand. Now, before we leave triangles, I want to mention something called the triangle inequality here. And essentially what this is saying is that if you have a triangle, and we'll specifically talk about right triangles, but we could make it more general, actually. Let's say A, B, and C. It turns out that each of the other sides has to be less than the angle opposite the largest degree. So there's a few things we can say from this. These are all not the triangle inequality, but I'm going to mention a few things. First of all, A definitely has to be less than C, and B definitely has to be less than C. The question is, what about A plus B? It turns out, and this is the triangle inequality, it turns out A plus B is always bigger than C. And this holds whether you're talking right triangle or other kinds of triangles. Actually, maybe I should make it more distinct here. Like in this triangle, the longest side here is this one, so I'll just call it C. The other two are shorter. Here's an A and a B. But it still holds that when you add the length A to the length B, that length, total length, should be greater than C. As a simple example, if the sides of a right triangle are of length 3 and 10, what can you say about the hypotenuse? Well, I know that by the triangle inequality, that the hypotenuse, C, has to be less than 3 plus 10, or in other words, the hypotenuse is less than 13. I definitely know that. But there are other things I can mention, like if this is our picture right here, if I know this is of length 3, the hypotenuse being the side opposite the largest angle, the hypotenuse has to be bigger than that. Same thing here. If this side is side length 10, let's just say this is 10 and this was 3, I know that this side is opposite an angle smaller than 90 degrees. If it wasn't, if it was opposite an angle larger than 90 degrees, let's say this angle is 91, then you have two angles in this triangle, a 90 and a 91, and when you add them up, it goes greater than 180 degrees. So you can't have that happen. You can only have, at max, one 90-degree angle in a triangle. So I do happen to know that the hypotenuse will be bigger than 10. So we can do some estimations here on what the hypotenuse would be. But this is a pretty neat idea, that we know that it's between 10 and 13, somewhere in there. It might be 12.5, could be 11.993, something like that. Now, I sort of cheated on the last one because I was talking about an inequality without actually mentioning what an inequality was. An inequality is just a statement where you're basically claiming something's less than something else or something's greater than something else. And I've heard a lot of different ways to understand the symbols. I always say the best way to understand this is that the arrow points to the smaller item, right? And the large opening points to the bigger item. So if I see something like 3 and then there's a symbol and there's a 7, it means the smallest side of this symbol is pointing towards 3, so 3 must be smaller than, the bigger side is pointing towards 7. So 3 must be smaller than 7. It could be said equivalently like this. 7 is bigger than the small thing 3. By the way, the following is also true. 3 is less than or possibly equal to 7. While it's not actually equal to it, it definitely is less than. So that satisfies that. So these are the less thans and greater thans or equal tos. And these are considered, right here, are considered to be strict inequalities. In other words, you can't have equality there. They can't be equal. It's just strict inequalities. All right. Now, before we can actually solve anything involving inequalities here, and I'm not going to delve too much into it, I just want to mention a few, maybe like 3 theorems here, and then we'll get back into some geometry. It's just because we just happen to touch upon some ideas within, or ideas involving inequalities. It's probably good to mention this stuff. So, first things first. If A is less than B, so if I happen to know I have an object that's smaller than another object, then I can add or subtract a number from both sides, and the inequality will still hold. Oops. So I add or subtract C from both sides, that inequality still stays the same, it still holds. For example, if I told you that 5 is less than 18, or less than or equal to even, then me adding 10 to both sides doesn't change anything. 5 plus 10 is still less than or equal to 18 plus 10. Essentially, what you're doing when you're saying that is on a number line you have 5 and you have 18. And what you're saying is I'm going to grab that 5 and I'm going to shift it over 10 units all the way over here to 15. Well, at the same time, you're going to grab this 18 and shift it over 10 units as well to 28. So obviously, the number that was 18, which is now 28, is still bigger. You're moving them in the same distance. Same thing with subtraction. Okay. Now, the extra 2 theorems, it's actually 1 theorem, but I'm going to split it into 2. If, again, we start with a number less than another, and we happen to know that C is positive, then the following is true. A times C, well, that's still less than B times C. In other words, nothing changes when you multiply both sides by a positive number. A good illustration of this, just think of it this way, if you have, again, we'll do 5 and 18, right? And let's say I multiply both by 2. So I grab this sucker and I multiply it by 2. I grab this guy and I multiply it by 2 as well. On a number line, what this means is, let's say this is 5, and again, this is 18. Multiplying that 5 by 2 basically doubles it up, right? So it becomes 10. Multiplying 18 by 2 doubles that up. Now, let me give you an idea what I mean by doubles. The distance between 0 and 5, when I multiply 5 by 2, gets doubled, so it becomes 0 to 10. The distance between 0 and 18, when I multiply 18 by 2, doubles, and it hops actually further to the right, to 36. So notice the inequality still holds. 18 became 36, 5 became 10, but the inequality still holds because the larger number just gets that much larger. It still stays large. But there's something that happens that's slightly different if C was negative. So if you have two numbers, one less than the other, and C is negative, then A times C is now bigger than B times C. And let's not take, well, actually we can take, let's take 5 and 18 again. But this time let's multiply them by negative 2. And before I fill in the inequality there, I want to show you what this is going to look like. Here's 0. Here's 5. Here's 18. Now let's suppose I multiply 5 not just by 2, which would double the distance, but by negative, which not only doubles the distance, but flips it way over to the other side. So 5 gets multiplied by 2 to become 10, but then the negative takes it and flips it all the way over to negative 10. 18 gets multiplied by negative 2, so it shoots all the way over here to 36 first, but because it's negative, it hops all the way over here to negative 36. Now notice 5 became negative 10, 18 became negative 36. Now which one is to the left, or which one is a more negative number? It turns out the negative 36 is more negative. So when I have to point at the smaller or more negative number, I'm going to be pointing the different direction, the opposite direction, because the roles have switched. So it's a great way to think about it when you're dealing with inequalities. Let's just do a couple of examples maybe to solidify this concept. So here's a couple we're going to solve. Part A, again, it's just 3x minus 14 is greater than or possibly equal to a negative 21. When you solve these kind of like you would solve an actual equation. So I list out like what happened to x. Oh, first thing that happened to x got multiplied by 3, and the second thing that happened to x is it got subtracted from by 14. That's how they're hiding the value of x from us. So I'm going to undo those. So to undo the last thing, just like you would untie a knot, you always untie the last thing that's been tied. The last thing they did was subtract 14, so I'm going to add 14. And then after that, they initially multiplied by 3. I'll divide both sides by 3. So adding 14 to both sides is not going to change the inequality. So just add 14 to both sides, and you get that your inequality is 3x is greater than or equal to a negative 7. And now the second step here, which is dividing by 3, divide both sides by 3. I'm dividing by a positive number. So this means that the inequality stays the same. 3 over 3 is just 1, so 1x is greater than or possibly equal to a negative 7 over 3. That is the solution. Any x value greater than or possibly equal to a negative 7/3 will work. I'm not going to graph this now because that's not our job here. I'm just going to tell you that is the solution set. So 10. 10 is definitely greater than that, so that'll work. Right. Let's try an example B here. Negative 2 minus 7x is less than 12. What happened to x here? Well, the first thing that happened to x when they try to tie this up to hide what its values could be from me, they multiplied it by a negative 7. And then after they did that, they subtracted 2. So to undo that, I'm going to add 2 and then divide by a negative 7. That's my roadmap of what I'm going to do. So I'll start by adding 2 to both sides. And this implies that negative 7x is strictly less than 14. And now I get to divide both sides by negative 7. Negative 7 divided by a negative 7 is a positive 1. So we have a positive 1x. But now because I multiplied, or basically divided, both sides by a negative number, this inequality that was pointing towards x now points the other direction. And 14 divided by negative 7 is a negative 2. So that's a quick and dirty introduction to inequalities, or review of inequalities. But it was only there, I only did it because the fact is we did the triangle inequality, so I kind of had to throw this in here so that you would understand everything. Now to get back into the geometry here, let's just talk about similar triangles really quickly. Actually, you can even do a definition of similar figures. Two figures are similar if their shapes are exactly the same, but their size may actually be different. So one might be 3 times the size of the other, but they have the same exact shape. A good example of this is like a stick figure. That's probably good. This stick figure, if I can draw it exactly the same as this stick figure, let's see if I can do it. Okay. Those two figures are similar because they're the same exact shape, it's just one's twice the size of the other. Okay? And if you have similar objects, then you can say quite a bit about them. So I'll do this through an example because again, this should just be a review. So in this example, we'll take something realistic. All right. So this is a sand sculpture on the right hand side here. Suppose you're trying to determine the height of the sand sculpture, but you're not allowed to get too close to it. Maybe they fenced it off or something like that. Now you notice the shadow it casts reaches the fence you're standing at, and the guide who's with you tells you that this distance between the figure and the fence is 10 feet. Let me just draw this out so you can see what I'm talking about. I'll just do this. So you have some figure here, even though their figure is much prettier than mine. It's casting a shadow that is 10 feet long. Okay. And let's assume that's a right angle that figure's at. Okay. At the same time, you quickly busy yourself and have your friend measure your shadow. So here you are, right here. And your friend measures out your shadow, and you know you're 6 feet tall, by the way. And your friend measures out your shadow and says, oh, that's 8 feet. By the way, we're assuming you're standing at a right angle. Okay. We're going to use this information to figure out how tall this sand sculpture is. Well, this is how you can do it. If it's a very exact same time of day, then the sun is casting the same through the same angle, a shadow through the same angle. So this angle will be the same as this angle right here. So these triangles, if they have two angles that are the same, these triangles have to be the same shape, right? They have two 90-degree angles, and then they have this top angle and this top angle exactly the same. So therefore, these two triangles must be similar. The only thing I don't know is this height. You can use that argument that h is to 6 as 10 is to 8. In other words, you're creating a ratio, a proportion or a ratio between these two objects. So h is to the side length, or the height of the figure is to your height, as the length of the shadow for the figure is to the length of the shadow of you. So figure to you, figure to you. Okay. And you could solve this just by multiplying both sides by 6, and you'll get that h is equal to 60 over 8. This can reduce, right? I think both are divisible by 4, so that's 15 over 2, or 7.5. So this figure is 7.5 feet tall. Roughly, because probably your friend made a mistake measuring you, and obviously it's probably not exactly 10 feet, but you get a rough estimate there. It's pretty good. that's what we do with similar figures, is we create a proportion that we can solve. And we'll go ahead and finish up this lecture with a talk about areas and volumes and surface areas. And essentially there's going to be some basic shapes we're going to talk about, and some of them, most of them you should know. For areas, let's see, how do I want to do this? We'll do like rectangles, length times width, right? That's the area is equal to length times width for a rectangle. But then you have an equivalent object that depends on who you talk to. A cube, but if it's a cube, all sides must be the same length. So we're going to say a rectangular box here. If you can imagine the three dimensions kind of appearing before you. Okay, that rectangular box has a length, a width, and a height, and the volume of that would equal length times width times height. Really, surface area has to do with volume, or it has to do with three-dimensional objects. It's like, how much wrapping paper do I need to cover this surface? So the surface area, I don't like to memorize a formula. Instead, I just like to think about it. I mean, really, you have a side that, let's start in the front and the back, okay? The front has a width and a height, and so does the back. So you have two width heights. And now you have just the two sides and the top and the bottom. So the two sides have dimensions length times height and length times height. So we'll do that one. And then the bottom and the top have dimensions width times length. So we have two of those, width times length. Okay. So that's really all there is to rectangular objects. Triangular objects, we're not going to get into a volume of a three-dimensional triangle, but the area at least is 1/2 base times height, where this whole length right here is the base, and this center altitude is the height. Then you have circles, and the area of a circle is pi r squared. Pi is not 3.14. Pi is pi. Just have to say that. Okay. And then you have a three-dimensional circle, which we call a sphere. Okay, I'll just draw kind of a belt around it so you can see it's a three-dimensional sphere. And the volume of a sphere is equal to 4/3 pi r cubed. The surface area of a sphere is 4 pi r squared. Now, I don't know who your instructor is, and if it's me, I'll just let you know. I don't have people memorize at this level of the game volumes of spheres or surface areas of spheres. It's a little too daunting and unimportant. I could always Google it. In fact, surface area I don't have memorized. I Googled that just right now. I paused the video and did it. And then another kind of object here is a cone. And that has something to do with, I guess, a triangle. So maybe I'll make a three-dimensional triangle like this. I'll make a cone. So we have a base that's like a circle here. And, oops. And we have this, where we have an altitude we'll call the height. And here we have a base. And I don't know if we'll need the base or the radius for this, but we'll find out. Now, the volume of a cone, like a traffic cone, is 1/3 pi r squared h, where r is actually the radius. So this little distance right here is the radius. And I didn't mention it for the circle, but this distance is the radius, and in a sphere, again, halfway to the center is, or from the center out, is called the radius as well. Now the surface area for a cone is equal to pi rs plus pi r squared. Now you're probably wondering what s and well, actually just what s is. S is the length of the edge. It's the edge length here. And the components are, this is actually if you're going to coat the side, and this is from coating the bottom, I guess you could say. So sometimes you don't want to coat the bottom, just leave that off. If you let's say you have an open cone, in other words the bottom is not there, then all you need is this part. But if you're coating the sides and the bottom, then you'll use this entire formula. Now let's just do a single example here, because areas and volumes and surface areas, you could do tons of examples. So I'll just do the one. So suppose the following cone is 6 inches tall and the scoop on top forms a perfect hemisphere. That means a perfect semicircle. Okay, so it's half a circle up here, or a half a dome. Okay, I know the height from here down to here, they tell me, is 6 inches. And this is a perfect hemisphere, and let's pretend it's a hemisphere of radius, because I didn't put a radius on there. So let's say of radius, well, let's say 2 inches. Okay, so that means the distance from here to here is 2 inches. All right, so what is the volume of ice cream that can fill up this cone? That's a volume question, right? You'll need to know the volume of a sphere, of half a sphere. So let's start there. Volume of a half a sphere is going to be half of the volume of a sphere, which is 4/3 pi r cubed. Doing the math a little bit, the 2 and the 4 cancel nicely, so we get 2/3 pi, and then the r here they tell me is 2 cubed. 2 cubed is 8. 8 times 2, 16, so that's 16/3 pi. So I know the amount of ice cream just sticking out the top is 16/3 pi. Now I just need to know how much ice cream is in the cone itself. And this will take me just hopping back here and finding out what the volume of the cone is. So I have a cone right here. The volume is 1/3 pi r squared h. 1/3. So the volume here of cone equals 1/3 pi r squared h, where h is the height. That's 1/3 pi, and the r here, the radius of the top, is 2, and the height is 6. Let's see, it's 4 times 6 is 24, so we have 24/3 pi, or in other words, 8 pi. So altogether, the volume of the ice cream is 16/3 pi plus 8 pi. And you can grab a calculator, because at this point in the game, we're not really too concerned about combining like terms on something like this, although we possibly could. 16/3 times pi, notice I'm not multiplying by 3.14 because that's not right, plus 8 times pi. That's 41.9. Let's round to the nearest tenth. So 41.9. 41.9 what, though? Oh, I see, these were inches. So this, and remember, volume is cubes, so it's cubic inches. A couple ways you could write that, either inches cubed or cubic inches. Last question is a bit of a challenge. If you dip the entire cone with the ice cream in a chocolate coating, how much would be used? That's a surface area question. Well, again, we have the surface area of half a sphere, surface of half that sphere. And I can't remember it, so I'm just going to go ahead and look back a page here. The surface area of an entire sphere is, where are we? Surface area of an entire sphere is 4 pi r squared. So let me go ahead and write that in. Oops, I went the wrong way. So we have half a sphere, but times 4 pi r squared. which would reduce to 2 pi, and then r is 2 squared. So that's going to be 8 pi. So that's how much chocolate I'm going to use is on top. And then the surface area here is going to be tricky. For a couple reasons. If you remember the formula, surface area of a cone, we're not going to include the bottom, okay, because we're only going to coat the sides. It's pi r times s. So let me go ahead back there and just put pi r s. And we happen to have r here, it's 2. But we don't have s. But guess what I have here? This is a right triangle. So I could find out what that length is. This length, which I'll call s, I could find because 2 squared plus 6 squared should equal s squared. Or in other words, 4 plus 36, which is 40, should equal s squared. So in other words, s should equal the square root of 40. I'm not worried about reducing that for anybody who knows how to. I'm just going to do it this way because I haven't talked about radicals yet. So it's 2 pi times the square root of 40 is the surface area of the cone. So the total surface area is 8 pi plus 2 pi root 40, which will roughly equal, well, let's find out. Let's bring up our handy dandy graphing calculator. And let's see, this is 8 pi. And let's see, plus 2 pi times the square root of 40. 64 point, again, 9, round up, nearest tenth, 64.9. And this is surface area. Areas are square, so inches squared. Square inches. That's how much chocolate we'd put on top of that. I'm hungry, so I'm going to go eat dinner.